Last week, we completed the study of transport layer with an open question. The open question is, why is it a good idea to do retransmission of lost packets in the end systems and not hop by hop? And we have seen that there is a good argument for that, which is the simplicity of the intermediate systems. But now, what we would like to see is whether from a performance viewpoint, this makes sense. For this, we need to see a simple elementary result of information theory. If we take as metric of performance the throughput of a communication path, and in this very academic simplification, if we assume this path has a transmission rate of capital R in packets per second, for example, and if we lose a fraction p of the packets, then the capacity, in the sense of information theory, is R1 minus p, which means that the useful throughput, if you have a very smart coder, will be arbitrarily close to this value. That's a very simple result if you think about it. That means if you have a channel at 1 gigabit per second that loses 10% of the packet, then you can have 900 megabit per second of useful capacity on this channel. So let's now study the capacity of an end-to-end path with the two options, whether we do hop by hop, loss recovery, or end-to-end. Right? So to simplify the story, I assume a single channel, which is a sequence of links, and every link has the same capacity and the same loss probability P. In fact, it's not going to be like this in reality, but let's assume this to simplify the analysis. Right? What are the formulas for the end-to-end capacity in the two cases? In fact, I'm asking you now, in one case, if we do hop-by-hop error recovery, so if a packet is lost between R2 and R3, we repair it locally. And if we do that at every link, how much capacity do we have from A to B? So if each of the links has the same rate R, drops a fraction P of the packets, what is the capacity that's available from A to B? That's the question to your sagacity now. I close the poll in 5 seconds. And you see the results. The majority says A, but this is wrong. If we repair losses at every hop, the capacity of one hop is R discounted by 1 minus P. So we have a sequence of n hops. Each of them has the same capacity, R minus 1 minus P. So the end-to-end capacity is the minimum of those capacities. It's a piping result, if you want, of information theory. If you put in sequence a number of tubes or pipes that can sustain a throughput of R1 minus P each, then the sequence has exactly this capacity. So the capacity of the end-to-end path is exactly this, right? Many of you have given this formula, which is in fact, if we do end-to-end recovery, because if we do end-to-end recovery, and if we assume that the loss events are independent in each of the links, then the probability that the packet is not lost is 1 minus P to the number of links. The probability that it is lost is 1 minus this, and the capacity of the path, which is 1 minus Q, is this here. So we discount the capacity by 1 minus P at every hop. If we have K hops, we discount by 1 minus P to the power K. So that's the capacity value we obtain if we do end-to-end recovery. If K is equal to 10 with those two different packet loss rates, those are the values we find. Right? If 5% is the loss probability, on 10 hops, the end-to-end throughput is 60%. We have lost 40% by doing end-to-end recovery, because the probability that one packet is lost somewhere is 40%. If the loss probability is 10 to the minus 4, this value here, then the capacity is this one here. And in hop by hop, the capacity is 1 minus this probability. are the values given here. This contains, in fact, all the take-home message, this chart. It explains exactly what happens. If you have links that have high loss probability, although 5% is not very high, but for a communication network, it's considered high. If you have 5% loss probability, you probably should not do end-to-end loss recovery. If you have very low loss probability, then it doesn't matter. Either way, it's lost in the noise. What does that mean concretely for the internet? If you had to design the internet from scratch, what would this tell you? Is it a good idea to do like we do, to detect losses only at TCP and repair them end-to-end?
If the packet loss rate is very small, so we should ensure that the packet loss rate is very small.
Yes, so that makes sense only if the packet loss rate is very small, which occurs typically either because we have a congestion control that prevents buffer losses, and that the transmission errors are rare. Transmission errors on cable system. So this makes sense on cable systems. Now, do you know systems where there is no congestion loss, but there might still be non-negligible probability of packet loss? Well, this is typically wireless systems, Wi-Fi, other forms of local wireless systems, or cellular networks. In such networks, it's very hard to know exactly what are the parameters of the channel and to do the coding to guarantee that there would be very little loss, in particular if you're moving in a car or walking. So this will typically happen in wireless channels. So on wireless channels, you should do hop-by-hop recovery, right? This is why in Wi-Fi, there is an acknowledgement, and when you send a packet to the base station checks, sends you an acknowledgement. If the packet is lost, you will resend it. So the MAC layer, in the cases where the loss probability is not negligible, should do hop-by-hop recovery. That's the take-home message for the internet, and this is in principle what is done. Wi-Fi and cellular network have mechanism to check that a packet is not lost. Some systems sometimes include some hidden error recovery. For example, there might be systems that if they know the packet loss here is not negligible, they will retransmit the packets for you, even if they are not necessarily wireless. Voilà, that's what we will say today for the transport layer. We will come back to the transport layer a bit later in something that I put in the application layer, even though it is really, truly a transport layer. There are alternatives for doing what we do. So we've seen that the transport layer of the internet is TCP or UDP. Other than that, you have no choice. But if you are curious and you watch what you do when you use Google software, for example, you will see that many systems don't use TCP, they use QUIC instead, which is a framework to substitute to TCP. But the good news is everything it does is practically the same as TCP. We'll come back to that a bit later. Before that, we will need to discuss of congestion control, which will be the topic of the module in 2 weeks. Any questions on the transport layer so far? No, if there is not, we move on to a topic that is visible from the lab assignment that you have, multicasts. Multicast, something we have encountered already. We have seen multicast addresses. In particular, IPv6 is very fond of multicast addresses in link local mechanisms. Multicast addresses, I should mention that here. Multicast exists at the IP level. It's very old. It's at least 25 years old. Very popular in things that we normally don't see. For example, in automation substation, in factory automation, in internet or MAC layer communication for machines. It's also used by Swisscom and other companies for doing TV streaming. That was the idea of multicast. It was If you have a large number of hosts that are receiving the same thing, which is the case for TV or radio, then you can distribute that over the internet instead of distributing that over the broadcast systems that are dedicated to radio and TV. This has existed for 25 years, has not become very popular in the internet for a number of reasons that we will discuss. One of them is certainly that you do a lot of on-demand TV. So if you go to YouTube, you're not multicasting. Not everybody is watching the same thing, even though in reality we are all watching the same things, but not exactly at the same moment, so that the transmission is in fact point-to-point. Multicast uses special IP addresses, which are completely different in their use and their meaning than regular IP addresses. For IPv4, those are the address that start with 224, so 224/4, that means anything in that range. And for IPv6, it's anything that starts with FF. Right. An IP multicast address is used to identify a group or a channel, if you want to think of it as a TV distribution mechanism, which was really the intention at the beginning. It exists, unfortunately, in two flavors that make it a bit complicated sometimes to describe, but the ideas are very simple. The original idea of multicast was to do any source multicast, which means the channel or the group is identified by the multicast IP address. And anybody could send to this address. Of course, the anybody can send to an address makes the thing a bit hard to manage. In particular, when this was done, we were in the world of the early days of the internet, where security was not really a concern for many people. Now security is a concern, so most networks verify who is sending which packet to whom. With any source multicast, the door is open and makes the verification more difficult. Source-specific multicast is similar, but the identity of a group is the combination of a source IP address, a regular unicast address, and a destination multicast address. That's the differences here. For some reason, the IP addresses that are used for any source multicast or source-specific multicast, they belong to different blocks to make sure everything is easier. Here is one slide showing practically everything we need to know about multicast. So I'm illustrating a little cartoon where I have a source here and two receivers, A and B. In multicast, sometimes the language is a bit different. Sometimes people call S the talker and A, B the listeners, which is really illustrative of the fact that multicast sending is really based on the principle of subscription. Somebody sends messages or streams of information, and those who want to receive, they subscribe and they decide to listen. Just like by the same way you tune to a given channel on a radio, old-style analog radio program. So here, let's assume S wants to send, then in principle, there's nothing else to do than to send. So to send to a multicast group, all you need to do is create an IP packet with destination address, a multicast address. So in the sockets, all you need, if you use sockets, all you need is to give a destination address that is a multicast address. I say all you need is, well, in fact, if you do only this, it won't work because your socket software will verify whether the destination address is multicast or not. If it is multicast, you may need to instruct the socket through socket options to allow it. But in principle, that's the only thing you need to do. You send to the multicast address. This is very illustrative of the way multicast was designed. It's made to make the job of sources easier. Your Swisscom and you stream a TV program to 1 million receivers. All you need is one server, perhaps two for reliability, that sends one packet for each video stream. Right? Now, if nobody has registered, nobody is listening, this packet will die. Right? The router here will not receive it. It will be sent over the local area to a multicast address, but nobody has subscribed, nobody is listening, so this packet is dying. By the way, you can test that. There are famous applications like iTunes in the Apple devices. They do that at home. Inside the local area network, you can multicast your audio or video, and it will die if no one is listening. If somebody is listening, then others might receive it. Now let's assume that A wants to listen. Then A needs to do something active, so the listener needs to subscribe. With IPv4, subscription is activated with what they call the IGMP protocol, Internet Group Management Protocol. So if A wants to listen to the channel sent by S, A needs to know what is the channel by DNS or by going to a website or some out-of-band information. That's the usual problem. If you want to go to a server, you need to know somehow the name and from which you will get the address of the server. So here, assume it's source-specific multicast. So A wants to join to a channel that is sent by S to the multicast address M. So A will send an IGMP message which is sent to the multicast router that serves the LAN where A is. So that message is not sent to the source, it's sent to whoever is a multicast router on my LAN, and hopefully will manage to get that information for me. When the multicast router receives this, it keeps state information. State information is things like, there is somebody listening to SM on my interface, which is here on the west, and then it needs to create a tree, a distribution tree. We will talk about it in a minute. So here it creates it by contacting R2 with a, now 3 is a routing protocol, a multicast routing protocol. PIM is the most widely used. So R1 will activate PIM and send a message to R2. R2 will say, oh, there is somebody who wants to receive SM. How do I get SM? So R2 will continue creating a distribution tree. So there is a recursive creation of the tree, and R2 will talk to this R5, and R5 now keeps state information. This red block means those routers are remembering one thing. There is somebody listening to SM, and they have to send it on the corresponding interface. So that now, when S sends the new video frame, for example, the frame will reach A. Right. Notice the difference with IP unicast. With IP unicast, the routing information is quasi-static in the routers. It's dynamic, as we will see in 1 hour, because the goal of routing protocol is to react to failures and changes of origin. But as long as the network is the same, the routing information is completely stable. You don't do it whenever somebody wants to listen. In multicast, it's very different. There is state information here that is specific to the fact that A is listening to SM. And that state is available, has to be available everywhere in the network. That makes the routers way more complicated than for unicast, which is one of the reasons that it's not so widespread in the internet today. Now we have seen only one destination, which is not very funny for multicast and depressing for the popularity of S. So let's assume B also joins. So B joins, so the same thing with IGMP will happen. R4 will create a branch of the tree, will contact R2, and R2 is a point where the two branches are merging. So at this point, R2 has nothing to do other than remember had the control block for this interface. Now it has it for its west and for its south interface. But it doesn't need to propagate the information further to R5 because the tree is already built between R5 and R2. That is, of course, the main idea of multicast. And now, when a packet is sent by S, the packet is duplicated by R2. Routers like R2 that have several multicast entries for the same group will do the duplication. Here. And now the two packets will arrive. So that's the idea of multicast. The idea of multicast is sources send only one packet to the group, and it's the routers on the path that do the multiplication. Now that may seem, why is it interesting? Somebody has to do the multiplication. But why is it more interesting to have the routers do the multiplication than the servers? Yes?
Because the idea of multicast is to make the work of the source easier.
Mm-hmm. Because the idea of the multicast is to make the work of the source easier. But if you make the source, the wake of the work of the routers as difficult as it would be for the source, probably you could say it's a bad idea, because a router is not a server. A router is something that needs to be real-time and is more performance constrained than a server. Yes?
We also have less congestion. We have only, let's say, we send it to R5, then one only to R2. We don't have like two twice to send to R5 or to R1. But we send only one packet to R5, then for R2 only one packet, not twice over. And that's really the...
Yeah, that's a good observation. Here we reduce the traffic. Here on the backbone of the network, we reduce the traffic. If we have 1 million users at the end, the first hop here will have only one packet, not 1 million packets. There's another idea, is that if you yes?
Maybe if the server has to do one message sending destination, it will be very long. As for a router, you just have to at most send the packets once on each interface, and it will treat it.
Exactly. So a router will need to multiply the packet only by as many times as there are interfaces, which is not millions, but is perhaps in the very powerful routers, perhaps hundreds. But if you do that several times, if you have on a path in a given tree of depth 10, and if you have if you have routers that each multiply 10 times, then you have 10 to the power 10 packets here. So that's the beauty of exponential growth. And that's the main idea of why multicast is more efficient for example, TV distribution networks. I mentioned that the routers must keep multicast information. So this is, for example, the type of information it must keep. We mentioned the outgoing information that's used to know where the traffic has to go. But typically today, you also have additional information on where it's supposed to come from. Of course, multicast is a potential security problem because of what? Yes?
Denial of service.
Denial of service. If you want to congest links, now multicast is more efficient from a congestion viewpoint, but from the attacker viewpoint, it's also more efficient. If you want to reach 1 million users with one single packet, and you can do that, then you can congest those million users by sending 1 million packets to 1 million multicast groups, and then you will bring the network down. So multicast is a problem, and most providers in public networks don't support multicast. So if you try to do the part of the lab that does multicast, if you do it in a public network, it will not work. I think that's as far as I know, Swisscom, Sunrise, and the like, they will not support your multicast traffic. On the EPFL network, it works, but that is very special. Another aspect of multicast is the lack of aggregation. Here, one beauty of IP, which is particularly visible with IPv6 more than IPv4, because with IPv6 the addresses can be nicely packed together, is the aggregation. Here, for example, this router has a single entry for all addresses that start with B, which is all of this world here. Right? If you do that for multicast, then this might not be the case. For example, if Homer here listens to M1 and M2, but Bart listens to M2 only and Lisa to M2 only, this router will need to know separately that there is somebody from M1 and M2, and where this guy is that listens to M1 and M2 is completely independent of the IPv6 or IPv4 address aggregation. So they can be anywhere. So you need to keep state information for all multicast groups, and there is no structure in this. So that's another reason for making multicast not scalable at the scale of the entire internet. Is there multicast ARP? That's a question we were already confronted with, and we have seen, in fact, on some examples that there is not. ARP, in principle, is finding the MAC address that corresponds to an IP destination address, and this is done typically by asking either the destination, what's your MAC address, or by asking the local switch, if we do DHCP sniffing, for example. In multicast, it's very different. So the MAC multicast addresses are deterministically computed from the IP addresses. For some reason, there's a different prefix for IPv6 and for IPv4. So if you have an IPv6 multicast address, you take the last 32 bits of the IPv6 destination multicast address, and you put it into the MAC address, and that gives the MAC multicast address. And we have seen the use of it when we spoke of, for example, the solicited node multicast address. This is how it's built. For some reasons, for IPv4, it's 24 bits, and only the last 23 bits, in fact, are used explicitly here. Don't ask me why, I don't know. How does the multicast happen at the MAC layer? At the MAC layer, there is a problem. That for multicast to work at the IP layer, we have seen that there must be two things. There must be a subscription protocol, which is IGMP for IPv4, MLD for IPv6. So there is a protocol between a host and a router, where the host says to the router, I am subscribing to this group. And then there's a routing protocol, a multicast routing protocol between the routers. At the MAC layer, ideally, we would need to do the same thing. So there would be the need to be a MAC multicast group subscription protocol, but that doesn't exist. So what is done today is, in many cases, the non-smart switches, they simply treat multicast as broadcast. So whenever there is a multicast packet on such a switch, it's sent to everyone. Now, the network card has the instruction which multicast address it's subscribing to, MAC multicast address. So if B is listening to this address here, then it will not be received by those who do not listen to it here. If B and C are listening, the network adapters will not throw it away. Here they will keep it. So that's one way of doing, which in passing is amusing because it means if you have IPv6, that takes a lot of effort to make multicast packets instead of broadcast. In fact, they're still broadcast to everyone here. The difference is probably with Wireshark, you will not see the packet here because it will be deleted by the hardware already. The smart switch, because there is not a MAC layer protocol for group management, will simply overhear the group management protocol of IPv4 or IPv6 here. So so-called smart switches listen to the IGMP messages. So if this guy is doing an IGMP message, it will send it to whoever is a router in the domain. Perhaps there's no router, but the message will be overheard by the switches, and then the switches can build a distribution tree, or at least decide, because the switches already have a tree, right? Which one? The spanning tree. We've seen that the bridges, in principle, build a spanning tree. So there is a tree already in place between all the equipment. So they can use this tree to forward the multicast, but they can decide to prune, that means to delete, to not send on the branches where nobody is listening to. So this is what is typically done today, which is very embarrassing, but is how things are in the internet. It's another instance where the nice layered architecture that I'm teaching you is not really what happens. First example was the NATs, for example. We see that NATs do address translation by looking at TCP port numbers, which is a bit weird. Here we have another example where a MAC layer thing looks at the IP layer messages to do its job. But this is how things are. Multicast routing. I mentioned that the routers, they need to compute a distribution tree. So this is both a very simple and very complicated topic. What we will see is the simple part. It's very complicated because there are lots and lots of possible multicast routing protocols, and you don't know exactly what will be implemented by whom, and they are not compatible. But something that is very frequently implemented is called PIM sparse mode. PIM stands for Protocol Independent Multicast. What does that mean according to you? Why independent of what? Yes?
The IP version.
independent of the IP version. We wish it would be the case, but it's not the case, unfortunately. It's independent of the point-to-point routing protocol. So here I'm doing a forward reference to what we will see in an hour, but I've already discussed the fact that the routers must run something between them to compute the routes. Right? They do this for the regular IP addresses, not for the multicast. And the idea of PIM is to use this information to construct its own tree in a way that is completely orthogonal, independent of which specific method you use to build the routing tables. Whether you use OSPF, like we will see, or RIP, like we will see at the end of the course, or IGRP, which is the Cisco version of distance vector, or you do SDN kind of ad hoc configuration. It doesn't matter. PIM is independent of that, and we'll see why in a second. There's PIM sparse mode and dense mode, but as far as I know, PIM sparse mode is the only one that's really is implemented today. And in the case of single source multicast, it's very simple. Let's see here. If we have, for example, this router that has received the job of building or triggering the construction of a tree for distributing the packets for the group SM. It's source-specific multicast, so the group is explicitly saying this group is only for packets that come from the source M. Then what it will do, it will send a routing protocol message, which is called in this case a PIM join message, towards the source using the classical routing tables that are present in the routers. S is a unicast address, so it will send this message to the next hop of R1 towards S, which is R3 here, R2 here. R2 will do the same thing here and will send it to R5, and therefore this is how the tree will be built. And similarly, R4 will send to R2. So it's using the reverse path. It's called reverse path forwarding. And the routers, when they receive those special messages that are routing protocol messages, will create the data structure that we have discussed a minute ago. So it's very simple. If you're interested in the other cases, you can dig them out. I mentioned that, I will skip it. So in practice, as I mentioned, multicast is used primarily in industrial networks and for internet TV distributions. Some corporate networks use it, for example, to save the bandwidth when you distribute news. In an airport, when you show the same display on thousands of terminals, then you can use also multicast to send the same display. And then networks that have the luxury of supporting things for research do it as well. Of course, as we have already guessed with TCP, multicast doesn't work because TCP needs to receive acknowledgement. If you have 1 million receivers, you will be flooded with a 1 million acknowledgement, and we have discussed ways of alleviating this problem. So multicast mandates the use of UDP. It works only with UDP, which means you will have to do your own retransmission using schemes that I've discussed before. For internet TV distribution, you typically don't do repair of losses. If there is a loss, you see it on the screen. You see a frame is missing, a new frame will be coming and will replace, you send 25 frames per second. So if one frame is missing, you simply hope that the other is not. If a group of frames is missing, you will see something visible, but you're not transferring a gold version of a movie to another machine. You're just transferring to people who are consuming them on the fly. So it is okay to have losses. So those losses are simply not repaired. In industrial networks, this is also typically what happens. You have sensors that measure a pressure in a tank, and you're controlling a chemical reaction, so you send the pressure every fraction of a second. If one measurement is lost, you don't have time to repair it, because by the time you detect and send another one, there's another reading that comes, so you prefer to use the newer reading. So same thinking here. If you distribute news on a screen that is refreshed every second, it's the same thing. And you may see that sometimes on some display system, you see the screen is frozen or doesn't work. But it doesn't matter, because the next second there will be a refresh that will send it again. So many applications simply ignore losses. Smarter applications for TV distribution use forms of source coding where they can, for example, send redundancy packets. One smart system that is used for coding audio or video consists in sending the audio and video coding with some resolution. Then in other packets, you send the same information coded with a lower resolution, so that if you lose one packet with some high probability, the information will be available in some other packet, but with a lower resolution. And if you have a smart decoder, it's able to mix all those things to have a flow that appears to be continuous with variations in the resolution, but we are able to ignore that entirely. If you see a video that has few resolution dips, you don't see it. As long as 90% or 95% of the frames are high resolution, you will have the impression it is high resolution. Voilà, we'll conclude on this little quiz. Question?
Yes, it's about the example that we saw. So there was one talker and two listeners, and the path was unique. And what will happen if there is several paths between the talker and the listener for in terms of trees?
So that's a good question. What happens if there are multiple paths? So typically the tree will pick one of them only. So the tree will not allow to have multiple paths. So if there would be multiple paths from R1 to R5, for example, then PIM-SM will have a way to decide for a rule that is consistently forcing R1 to choose always the same path. Here. So let's come back to the quiz. I close in 5 seconds. And then as the vast majority says, both B and C are true, which means F. Okay. Voilà, that's all we will do for multicast, at least in the lecture. In the lab, you will have to code your own multicast application and test it, which is also a useful thing for doing a small chat application, for example. Are there questions on this so far? Yes?
What about single source multicast? Because just one source can
So what we have seen is primarily single source multicast, but with single source multicast, it means a single source can send to this group, or in other words, a group has only one source. Which means if you have multiple sources, you have to have multiple groups. So as a listener, if you use single source multicast, you have to subscribe to all the potential groups, which would not work for the chat application, for example. For chat application, you have to use any source multicast. Right. Yes, question?
Doesn't the pin join
Doesn't the PIM join flood the server? No, the PIM join is a routing protocol message. So routing protocol is between routers. So the source will not see the PIM join. In fact, it will stop much before. It will stop at any point on the path where the tree is already built. So it's only the first guy who will go all along the way. Then for TV distribution groups, there is always someone listening to the TV, so the tree is already partly built, and most of the time what you do is just add a branch to come for the nearest router to come to you. But the protocol message, as I mentioned, does not go all the way here, right? When R4 sends a message, it stops in R2. It creates new state in R2, but it's not propagated further. Other questions? Then we move to the next topic, which is routing, unicast routing, a topic that will keep us busy for two labs. And what we will see is link state routing. Right? So this is illustrating a link state database. So it's a database which is present in every node, in every router when we use link state routing. So routing, I mentioned, is the way by which routers automatically compute the forwarding tables that they have. You can also place the forwarding tables by having a network management application talk to the routers and output the tables, but there is a problem with that method. Which problem? You have to manually do it. Well, you need a bicycle, probably. If you do it on the network here, you have a number of routers that go from Centre-Est to BC, and you need to go to every router to route the configuration. But how do you get into the router? In order to get into the router, you can put a web server in the router that will allow you to log into the router and talk to it. But in order to get to the router, you need routing table in the other routers that lead you to the path to the router. So you have a bootstrap problem. In order to communicate with routers, you need a path to the routers. And if the goal of communication is to establish the path, you need something. So sometimes you have a back channel. For example, routers have a GSM interface, and you can talk to them using a GSM interface. But if the only thing that the routers have is the network, you need a protocol that is completely self-organized, that runs in the routers and will find paths. This is what we will see after the break with OSPF. So we resume in 15 minutes. We're now ready to restart. So the topic is routing protocol. Just a small terminology issue. Routing is, like many words in this domain, are overloaded. So routing means often IP packet forwarding, means forwarding when it's done by looking at the IP headers, as opposed to other means of sending a packet, for example, only at the MAC layer. But in our context here, routing really means the protocol that is run between routers. So hosts are, in principle, not involved in a routing protocol. In the internet, there are so far, as far as I know, as far as you can find in the literature, there are 4 types of methods that have been used for doing distributed routing. So I'm excluding for the moment methods of routing that involve you going with a bicycle to every router and write some configuration information with a USB key or something. So distributed routing protocols, their goal for all of these protocols is you enable the software in a box that is a router, you connect it, and you do that in all the routers of your network, and they will automatically connect to each other and find paths so that you can comfortably be at one place connected to this network, and with your workstation you can access all the routers to do further things, and this network is operational. The first method that we'll see is called link state. It's not the first one historically, but it's the most widespread one in enterprise networks today. That's the one on which we will do the next lab. In link state, the idea is Google Maps, if you want. You have every router in a given domain, for example, in EPFL. EPFL is not using link state, but if it would be using link state, the domain would be EPFL. All routers obtain a map of the entire domain. A map means what are the routers, what are their addresses, what are the links between them, and what are the attributes of the links that are used to compute shortest paths, for example. So every link has a cost, and typically a cost is small if the link is fast, and large if the link is slow. This map is obtained by what we can call today gossiping. That means everybody says to everybody everything they know. We will see in detail how, or flooding if you want. This is how it works. And every router that has now the complete map does like Google Map. I want to send a packet from A to B. Which way should I go? Then I compute the shortest path on the map. And I use of the shortest path only the next hop, which I route into the routing table. So this is used by OSPF, which is the example we'll see in detail. And we will mention also a few other things that use it. IS to IS is a variant of OSPF, which is functionally, practically exactly the same here. So that is one method, which is historically not the first one because it requires that the routers have a disk to store a map that may be large in some cases. And so it's not for very small routers. Historically, the first method, as far as I know, that was developed is the one of distance vector. Distance vector is different. All routers in one domain know only who their neighbors are. That's the minimum information any routing protocol must know. And they know their distances to every destination. Distances is like, if I am in Lausanne, I want to drive to Paris, I can know the distance by looking the road signs. But in Lausanne, there's no sign for Paris. Let's say for Bern, there is a road sign somewhere in Lausanne saying Bern 95 kilometers. And by knowing only the distances and all the neighbors, it's possible to compute in which direction to go. That's using one algorithm called Bellman-Ford that we will see in detail when we talk about distance vector. And of course, for this to work, you need to share information. So the information that routers share with each other is their own distances. So a node will say to the neighbor, here are all my distances to all destinations. Now the idea of distance vector is if I am now a node, I can compare what all my neighbors say to me. If I have a neighbor A that says in order to go to Bern, from me it is 90 kilometers and I am 5 kilometers from you. If I have a neighbor B that says from me to Bern it's 100 kilometers and I am 10 kilometers from this neighbor, I know the shortest path is through the first neighbor. This is the idea of distance vector that we will revisit a bit later. It is smart in the sense that the information that is kept and that is exchanged is the information that you need anyhow. You need a routing table. So the only extra information is the cost. What's the cost to go there? So the routers have their routing table. You add to every next hop also the cost to the final destination, and that's the only information you need, and that's the only information you pass to your neighbors. Compared to this, where the information you have here is the entire map. So in order to go to Bern, I have the entire map, including all the details of the vicinity of Bern that I probably don't need if I want to be very compact. But as we will see, this is a bit tricky to make it work accurately. So today, many networks use link state. Other forms of routing exist in the internet. The third form that we will see in detail in the last lab, BGP, is path vector. Here, the information that is known by everyone is not a map and is not a distance, but is a path. For example, a path is, in order to reach a server in California from EPFL, I need to go through a sequence of what is called autonomous systems, which are the names of network domains. EPFL is one of them, Switch is one of them, Swisscom is one of them, AT&T is another one, Google is another one, etc. So you might have a sequence of paths. Well, Google is a bad example because Google is everywhere. But say if you go to a small startup company in California, the path would be EPFL, Switch, an international transit link, AT&T, and then a local ISP. So you will have all this information, all routers know all this information, and use it to compute optimal routes. Why they do that, we'll discuss in detail. but the essential idea here is that this is done globally at the global internet scale, where you care about where your packets go. You may want to send your packet through AT&T or not, depending on what happens. If you send a lot of traffic to AT&T, do you pay a lot? In which case you might not want to send a lot through that. Or if you're Korea and you send packets to Japan, you might want that your packets don't go through China, because in China they might destroy your packets if they don't like it, for example. We'll come back to that in detail. That's the topic of BGP. A last form that we will not see in detail, but I'll explain here in half a slide, is source routing. It's also called explicit routes. Source routing is a method where the routers essentially do nothing, because the route is written in the packet header. So here I'm showing a packet sent from A. So source is A. Sorry, this I should confuse. The source is A, and the destination is B. We should flip the two here. And the path is R1, R2, R4. That means that the job of A is in fact to send it to R1. And the job of R1, when it receives this packet, is to analyze the source routing information. It finds itself, so it looks for the next in the list, which is R2, so it will send it to R2. When R2 receives the packet here, it will send it to the next, which is R4, and when R4 receives the packet, it will look at the destination address, which is on link with it, so it will send it to B. This is used in what is called very old bridging systems, which is not routing, but is using similar things, called token ring bridging, or today in ad hoc networks. So if you have an earthquake somewhere and you have a group of 3,000 people who come for rescue operations, they build a network by putting wireless links everywhere and also some cable links. So they build their own network, and this is the kind of things you will use in such settings. We will not, so the protocol that uses that is DSR. It's also used in another context in MPLS. MPLS is something we will see popping up always on the corner. We'll not discuss in detail, but this is a backbone network technology for utilities, also for connecting private networks. With MPLS, what you may want to have is explicit routes that will work and are very robust. If there is any error or any bug in the routing protocols in the routers, then this will work as long as A and B are able to do correctly the route computation. Yes, question? Ad hoc network, why do we bridge or why do we route?
So why do we go to higher level instead of bridging? Because if we really know where should we go, should it actually go?
I can flip the question. Why should we use bridging?
I mean, we add somewhere that to which route we need to go. And there we would just rely on the physical address to get to know the code should be.
So that could be an option. You can build a bridge here and let the bridge do the thing. Very often there is an ad hoc support for mobility, so those things might move. So now you're connected to R1, but you move a bit and you're connected to R2 and R5. So with bridging, you need a sophisticated mechanism for this to happen. But you're right. I mean, there are always multiple solutions to do the same thing. This is the one that has evolved for that kind of ad hoc networks. A further idea of ad hoc networks is those devices might be also your own device. It's not necessarily a dedicated router, right? If typically wireless links, you're not able to go directly from A to B, but there are people that are in between and that are willing to serve as intermediate hops. This is the kind of things here that is used for. Of course, source routing doesn't say how the sources compute this. They put all the burden on the sources. How is this done? It depends on the protocol. For example, one way to do it is to flood the network by sending explorer packets. So if A wants to talk to B, it will flood packets. Flooding means I send to whoever is my neighbor R1 and R2. R2 will send them again, and you need a mechanism to avoid loops. And this mechanism, in this case, is path accumulation. When R2 receives this flooding packet, it will mark the path that the packet has taken, which will be AR2. If it sends it to R4, the path marked in the packet will be AR2, R4. If it sends it back to R1, then R1 will not send it back to A because it sees that by doing that, it would create a loop in the path. So this is one solution. That's a cheap solution that is used in typical things like DSI. As we will not see in detail today, what we will see is link state. Or we will start studying link state, and in particular, OSPF. There are two very widespread link state protocols, OSPF and IS2IS. They are very, very similar. They use a slightly different terminology. As far as I know, the most popular is OSPF. That's also the one we have in the lab because we have nice software that is very similar to what you would see on Cisco routers. So that will give you a good image of how things is in real network. We will study it in its simplest form, which is single area. OSPF is a hierarchical routing protocol that has two levels in the hierarchy. We will start by studying only what happens if there is a single level. In OSPF, so it's the idea of doing link state. So link state means everybody knows, every router knows its local configuration and will pass it to everyone. And conversely, will receive the local information from everyone. So what is this local information? Well, it is an interface and an adjacency database. Interface database is something you have statically, which is the interface, ETH0, ETH1, etc. And what are the IP subnets that correspond to those interfaces. The adjacency database is obtained by the Hello protocol. So Hello protocol is something you find in practically any routing protocol or any active distribution protocol. It is a ping, if you want, protocol that is used by routers. When a router runs OSPF on one interface, it will send a hello message saying, hello, is there another router on this interface? Another router that runs the same protocol as me. And if there is, then those two protocols will talk together, will discover each other. Those two routers will discover each other and will do a number of things that we will discuss in detail. They will synchronize their databases. And therefore, a router knows all the networks to which it is connected and all the routers that are neighbors of itself. That's the local information. Using that, it will flood this information to everyone and will receive flooded information from everyone that will allow it to create what is called the link state database or the topology database, which is the map of the network. The Hello protocol is used to discover neighbors, to create the map, but it's also used to react to failures. That's an essential property of routing protocols. The first property I mentioned was the plug-and-play property. You're able to bootstrap your network automatically without having a bicycle, although it's always nice to have a bicycle. But it's also used here to detect and repair failures. If a router breaks, then with the Hello protocol, you will detect that this router is no longer talking to you, or if the link between you and the router fails, you will detect that this doesn't work, so you will update the topology database of everyone. So after some time, all routers will have a modified map. It's like the analogy with Google Map is if there would be a failure or a blocking of a road somewhere, then you will receive a new map and you will recompute all the routes. When you create a network, in some very exceptional cases, you can boot all the routers together, but what happens most of the time, you boot them one after the other. So what happens in such cases is the Hello protocol is used to synchronize the link state databases. Synchronize here means one router already has a map of the part of the network that already exists. When a new router comes, it will not learn the map by the standard methods that run in stationary regime. Instead, it will copy from the neighbor. It will ask the new guy that's coming to the network, will ask the guy that's already in the network, give me your map. That's called the synchronization. Once this is done, then this new router can participate in the network. So in the lab, you will be able to see all those transitions in neighboring of routers. That is conceptually very simple, contrary to distance vector. That's a bit sophisticated. But as you will see in the lab, there's a number of details that make it a bit complicated practically. The terminology is important. So many things look similar, but it's important to know exactly the terminology. So a link state advertisement is the database record that a router sends to everyone and keeps from all the things that it has received. It describes what the local view of a router. So every router sends LSA that describes who the router is, its interfaces, and who it is connected to. The collection of all the LSAs constitute the topology database, or the link state database. Of course, as you can imagine, you need a way to manage the dynamic state of the link state database in a network where sometimes a router is added, sometimes it crashes, sometimes a new link is added. You need to be able to modify it. So this is done by a number of mechanisms that we'll see in detail. One of them is to have an age field where every LSA needs to be refreshed. If it's not refreshed after some time, it will die because a router that is alive is supposed to resend this information periodically. Similar mechanisms exist in all routing protocols. I mentioned PIM sparse mode last hour. PIM sparse mode sends join messages to create the tree. It has exactly the same principle. Those join messages are resent periodically, and if they expire, then the tree is rebuilt. Let's see on a toy example how things can work. So this is showing 1, 2, 3, 5 routers, 3 networks that are ETH LANs. The router's views, this is how the router's views the local area network, a shared medium Ethernet, even though today they are bridge network, but this is how the internet was constructed. And here I'm assuming there are also point-to-point links. OSPF will make a distinction between point-to-point links and shared medium network, as we will see in a second here. So at the beginning, if hypothetically we would boot all the routers exactly at the same time, which probably is not practical, but hypothetically, then every router knows what it is connected to. For example, router B knows it has an interface N3, which is an Ethernet, and it's called a stub. So a stub means here it's connected to no one else. N2 is an interface that is a point-to-point link that is connected to someone and is allocated a cost of 100, for example, by whatever rules you use in OSPF. You can manipulate all the costs using all the commands you want, but there are default rules that I mentioned. The faster the link, the smaller the cost. And N4 also has a cost of 100. So everybody has their local view. Then routers will do the hello protocol to discover whether a network is a stub or is connected to someone else. And at the end, so here is, for example, what B will do. B, after doing the hello protocol, will start flooding the LSA. So this pink box is one LSA, the same, which is shown everywhere, which is sent by B, so it contains its view, its local view. This one is sent to A and to C. Oops. So when C receives it, it will forward it to A, but A has already received it from B. There is a number in every LSA, what is incremented by 1 whenever you create a new LSA. So A will know that the message is receiving here is the same as the one it has already received, so it will drop it. You already have it. C will send it to D, and D will send it to E. So at the end, A, C, D, E have this LSA. And of course, the same will occur in all directions, so that at the end, all 5 routers will have this link state database, which is the same. So we have a replicated database in every router. It's not very efficient compared to distance vector. We reproduce a lot of information everywhere, but it has a number of nice properties that justify this inefficiency. So when this flooding procedure has converged, everybody has this information here. Now, if you look carefully, we have LSAs sent by B, router LSA sent from B. And there's a weird thing here. There's a network LSA sent from C. This is something that is typical of OSPF and is due to the fact that OSPF views the networks here as multi-point things, which they can really be. For example, here, this is an Ethernet network on which there are 2 routers, but there could be 3. You have a bridged network with some number of bridges. You can have 2, 3, 4, 5, a number of routers. Right? So one way to do it would be to say, well, I have one adjacency between A and C and whoever all the other routers are. OSPF does it differently. Instead, OSPF treats the network as a hidden node. So the bridge LAN, for example, the bridges that are not visible to OSPF because they are at the IP layer, they are not at the IP layer, they are treated as a virtual node that are called a network. So a network means a virtual node that stands for the shared medium Ethernet. Those ones, they don't have it because they have nobody connected to it, so OSPF ignores those in the first pass because they are called stub. So stub means they go nowhere. So for routing to a stub, all I need to know is to route to E. If I want to route to N7, all I need is to find a path to E. So in the path computation of OSPF, the stub networks are ignored. We just remove them when we compute the shortest path, and then we add the information once the shortest paths are computed. So they are ignored here. But this one is not a stub, so it will have a virtual node called a network. How does that work concretely? Concretely, there is an election protocol, a beauty contest, if you want, between all the routers that are neighbors and are on the same LAN. Typically, whoever speaks first becomes the winner, and it's called the designated router. So here, when C and A discover each other, they agreed that C is the designated router, which means that C speaks for N1. And in the OSPF mental model, C is a router that is connected to a network, and A is a router that is connected to the network, and the network speaks. The network sends a network LSA. So that's visible here. We see that A says, I am connected to N1, and I have a cost of going to N1, and the designated router is C, which means that the information about N1 will come from C, and this information says, I am N1, I am Ethernet, I have a cost of 0. The cost is 0 because A says the cost of going from me to N1 is 10, so the cost of going from N1 to something else is 0 by default. You can change it, but to avoid paying the cost twice, you make it 0 from the network to something else. And it is N1 that says I am connected to A and C, and possibly others here. If there is a large number, if there's only 2 routers, it's unnecessary complication. If there are 10 routers connected to the same LAN, then it's more efficient because only one of the 10 routers will centralize all the communications. Otherwise, you will have K-square communication if there are K routers in the same LAN instead of K here. So this is one little subtlety that is not essential, but makes OSPF so interesting. Now let's assume I plug a new router F to N7 and N1 here. What will happen is F7 will discover E or C. He will discover one of the 2 first. So let's say, for example, that F discovers C first. It might also discover A, right? So F will talk to C, will say, oh, I am a neighbor of C. Therefore, it will copy the database that C already has. That will take a large number of messages if the database is large. When F has the database, it is synchronized, and then it will flood to the network its own view of the world, which is essentially, I am connected to N1, and I am connected to N7. Now, N7 is no longer a stub, so N7 will also need to negotiate between E and F, who is the designated router. And in this example, the designated router happens to be E. So when those new advertisements are flooded to everyone, all routers, now the 6 routers, will have these entire topology databases that contains the router LSAs, for example, this router LSA from F saying I'm connected to N1 and N7, and somewhere there's somebody that must speak from N1, it is C, and somebody who speaks from N7, which is E here. So this is how the topology database is created and maintained. And if we want to speak of a graph, which we will need to for computing shortest path, the routers are nodes on the graph, but also the networks are virtual nodes. And in fact, here the fact that we mentioned already, the cost from going from router A to network 1 is whatever is configured on the interface. From N1 to C is 0 by default here. So this is the vision that OSPF has of its network. Practically, how does this work? OSPF is a routing protocol, which means routers communicate with each other. How do they communicate with each other? Do they communicate like an application? Do they use UDP or TCP? We will see that some routing protocols like BGP use TCP to communicate with each other. Here, OSPF does not, and it does not use UDP either. It is a special protocol that uses its own packets. So it has a protocol number. So in the IP header, there is a protocol number, which is 89 in decimal, in hexadecimal 59. So it's not using TCP. That means the reliable transmission has to be managed by OSPF. So OSPF has to implement all the bells and whistles that we have seen in TCP to repair packet losses. So when one router sends an LSA, it will wait some time for receiving an acknowledgement. So it sends it to a neighbor. The neighbor must send an acknowledgement. If the acknowledgement doesn't come, the router will resend the LSA. So it needs to manage all this. OSPF was originally developed for IPv4, and there are 2 versions of OSPF today. Unfortunately, ideally, I would like to be able to say there is one version of OSPF that supports IPv4 and IPv6, but we don't have that. We have 2 versions. If you have an IPv4 network that does not have IPv6, you can use only one version called OSPF v2 and one specific software. If you have an IPv6 network, you must use OSPF v3, and it will support also dual stack. That means it will support also the operation with IPv4 addresses, but it will require that everything is reachable with IPv6 here. OSPF, in the lab, we will play with 2. OSPF routers need to be identified for the shortest path computation. For example, I put a letter A. OSPF uses a 32-bit number. Guess why? Well, because 32-bit are the IPv4 addresses. The first version of OSPF, v1, which is now obsolete, was for v4, for IPv4 only. So originally it used an IPv4 address of a router, one of the interface addresses. If it's IPv6, it still continues to use a 32-bit number, which is interesting. So you will see 32-bit numbers that look like IPv4 addresses for IPv6 only routers. That's an OSPF router number. And we will see also that there are areas, but this is for future. So with OSPF, the idea is that every router has a topology database, which is at the end distilled into a graph. This one here. Then on this graph, OSPF will compute shortest path. So if I'm router A, I will to every network and to every router, I will compute a shortest path. Here. OSPF is typically associated with Dijkstra's algorithm. Why Dijkstra's algorithm? Because from many viewpoints, it's known as the best known algorithm if you want to compute all the shortest path from one node to all possible other nodes. So it's a polynomial time algorithm that is better than another algorithm that we will use for distance vector, which is Bellman-Ford, that does similar thing but has different properties. Every node has the same topology database, but every node computes different shortest paths because every node computes the shortest path from self to everyone. So the shortest path, with what is called the shortest path tree, is different. And if the databases are correct, then this is how we hope that there is no loop. Of course, if the databases are inconsistent, there might be loops. But OSPF has this synchronization property that is, before a router joins, it needs first to get exactly the same information as all the others, and from there, we send incremental information that cannot create loops. Here is the algorithm that is typically used in OSPF, at least a simplified view of it. It's Dijkstra's algorithm with multiple paths, equal cost paths. Dijkstra's algorithm is perhaps one of the most beautiful algorithms in an algorithm course. It's a greedy algorithm. It computes the shortest path in a graph by adding one by one nodes. And when the nodes are, so it constructs the shortest path tree, and when it first finds the first node that is the closest to self, and then it adds the second node, which is the one that has the second shorter destination from self, and the third, etc. So it always finds who is next in distance, and the beauty of it is that once this node is added to the tree, it will never change. And you will not need to modify the distance that you compute are final. Here is a version that supports multiple shortest paths. One of the interests of running OSPF is precisely this ability. Many topologies have a lot of redundancies. If there are multiple paths from A to B, it's a good idea to keep all of them. So OSPF has been designed from the beginning with the ability to find all the multiple paths. Of course, in a very rich network, you might have an exponential number of shortest paths. So you will not keep all of them. There is typically a limit on the number of shortest paths you keep, but the algorithm is able to enumerate all of them. So here is how the algorithm works. So the goal is to find all the shortest paths from self, which is node 0, to all other nodes, which are nodes I. M of 0, M of I is a tentative value, given what we know today, of the distance from self to that node. So M of 0 is always 0, and at bootstrap, M of I is infinite because I have no information. V is the set of nodes that are on the tree that I have built so far, so the visited nodes. Predecessor of E is the predecessor of I, is the predecessor of a given node on this tree here. Now, because we allow multiple paths, it's a set. Predecessor of E is a single predecessor if there's only one path. But if there are multiple paths to go to I, then it's a set with all the ancestors of I on the shortest path from 0 to I. So here is how it works. At every iteration, you will add one node. Which node will you add? You will add the node that is not already on the tree, and that minimizes the tentative distance that we have computed so far. And the beauty of this algorithm is that node that minimizes it, the M of I is the final distance here. We'll see in detail how, on an illustration how this works. Of course, you need to update M of I. How do you update M of I? Well, once you have picked this node, you look at all the neighbors of this node that are not on the shortest path tree, and you look at the distance that you have from self, from 0 to the node J, if I go through I. So I know the distance of going from me to I, which is M of I. I add the cost of the link from I to J. If this is better than the previous estimate I had, then I keep it. That's the shortest path. So I update M of J, and I add, and I say the predecessor of J is me, is I. If it is equal, I have found an equal cost path, so I add I to the set of predecessor of J, which, if M of J is finite, must have been non-empty. Let's see an example. So this is a simplified version of the network we had before. I've removed all the networks, the N, and because otherwise there are many, many nodes. So here I'm showing the view at A. This is a topology database. We are node A. So originally, the values of the distance from A to someone is 0 for A and infinite for everybody. And I have visited nobody, the set is empty. Then first step, I look for the node that minimizes the values. Of course, the first step is always the same. It's A, so I add A to the tree. So I visit A, I put it in pink here. And when I add a node, I look at what happens to all its neighbors. So the neighbors of A are B, C, F. And I have found a tentative distance from A to those three neighbors by looking at the distance I had, which is 0, to those. So the tentative distance to C is 10, to F is 10 over this link, and to B is 100. So I mark here, M of B is 100, etc. And I mark a predecessor. The red arrow says, so far, if the only information, if the algorithm would stop here, the shortest path tree would be predecessor of C is equal A, which means I would go from A to C, from A to B, and from A to F, which is indeed what I would do if I would stop now. So I update those predecessors and the M value. Then at the next step, I will look for a node that minimizes M. M is a tentative distance, not necessarily the final, but here, which one minimizes? We have two, C and F, so I pick randomly one of the two. For example, I pick C. So I add C to the tree, so now the pink is the tree that is built. We have A and C. And then, again, I update all the neighbors of C. Who are the neighbors of C? B, that was already visited, but I see whether it can be better, which is not the case here. I can have 110, so 100 was better. D was not visited, so I visit now a new node D, and the distance I found for D is 10 plus 20, which is 30. I can revisit F, but the distance would be 20, which is larger, so I don't take it. So I have here BF are unchanged. D has a new value and a predecessor here. That is what happens at step 2. So I have built a tree, and the property of Dijkstra's algorithm is that that's final. So C is at the distance 10 on the shortest path tree. In all the further iterations, things will not improve here. Next step, I find whoever has the smallest value of M, which is now F, so I add F. I look at all the neighbors of F. So there is C that is already visited, so I ignore it. I look at E. Visited means here on the tree. I look at E, which has now a new distance of 20, 10 plus 10, and a predecessor, which is F. After step 4, so we are here, what will you do? So can you do step 4? So the question I'm asking is, do step 4, and what are the state variables that are modified when you have completed all the operations of step 4? I close the poll. And the majority says F, but I think it is C. Oops. Let's see why. So here we need to pick the node that has the smallest M, which is E. So we add E. The value of the distance to E is not modified. The predecessor of E is not modified. But now we look at all the neighbors of E, which is only D. And the distance to D is not modified. We have found a new path, which is of distance 30, which is the same as the one we had before. That's an example where we have two paths of equal cost from A to D. We have this one and that one. Cost 30 for both here. So the M of D will not change, but the predecessor of D will change. Now the predecessor of D are two. There are two shortest paths that go to D, so we'll have two red arrows. The predecessor of D becomes C and E, which means that that's answer C, only predecessor is changed. Correct. If we continue then the next step is to add. So when we're here, the next to add is D. Whoops. When I add D, then there is no neighbors that was not on the tree, so there is no other side effect. And lastly, the last one to be added is B here, that will be at a distance of 100. Voilà, this is Dijkstra. You will see that it's very special in the sense that B is added at the end, for example, though it is one hop away from A. But whenever somebody is added, it's always in its final position. That's in contrast to Bellman-Ford, for example, that will compute shortest path by saying, what are all the paths that I can reach in one hop, then in two hops, then in three hops? And when I'll do that, at every iteration, the distance is modified. It's only at the end that we know the final distances. Now, what do we do with this? Once we have obtained this, the interesting thing is the red arrows, and by inverting the red arrows, we have the shortest path. So the shortest path is from A, for example, by reverting the arrows. If I need to go to D, I start from D, I follow the arrows, I found the path ACD in reverse order, and ACFE. So we'll have those paths here. What will OSPF do with that? Only one thing. It will write in the routing table in order to go, so that's the routing table at A. In order to go to D, there are two possible next hops, which are C or F, and the distance is 30. Voilà. We will continue exploring the beauties of OSPF next week.